Start. Okay, here we go. First of all, I won't see you tomorrow, but happy Halloween. Thank you. That's important. We are starting a new chapter, not quite yet, because I want to review some exponent laws first. Okay? So laws of exponents, because we are going to spend this chapter working through exponential functions and logarithmic functions, which are basically kind of the reverse of exponential functions. And that's what we're doing in this chapter. I would say it's my favorite chapter because, I don't know, it's just more fun than all the other chapters. But I'll let you guys decide what you like most. How about that? Chapter 2 is pretty good. Linear functions. Yep. I know, remember those? So nice. I have to move my ghosts because you can't really see them. Make them big. There. So, the exponent laws are on your formula sheet, okay? But I just want to take some time and go through them one by one. We've introduced them kind of on the slide because it should be review. But if it's not, right, I just want to make sure that we're all on the same page for this next chapter. Okay. So we're going to let A and B, and we haven't seen the set notation, but be in the set of real numbers, which is really just any number, right, that you want, any number that you can think of. And so here, really what this is saying is that, oh, sorry, in the set of positive real numbers, A and B can be any positive number, is what that's saying. Okay. And M and N are in the set of real numbers, which means that they can be any number. M and N can be any number. Can I just do the pound sign? Now, the laws are these. And let me just move this down. I've got some examples for us to work through. I think the first one should ring a bell, right? If you have a to the power of n, then that means a times a times a times a n times, right? And so that one should be good. But of course, now we're talking about these exponents, right? These powers. And so, so we have to remember what they do. As a fact, anything to the power of 0 is 1, okay? As long as a is not 0. Okay? And so if a is 0, 0 to the power of 0, well, I'm curious, should be 0 because it's 0 times, but I'm gonna, yeah, let's try it. 0 to the power of 0, math error, doesn't want to do it. I think because a and b have to be a positive number, so non-zero. Okay? But we also have when a is not equal to 0, so I guess it doesn't exist. Can't do it. So we've seen this one quite a bit before, right? Anything to the power of 0 is 1, and we've used that power or that fact with our polynomials, especially, right? With rewriting our coefficients and such. Yeah.
Wait, why does a have to be a positive number? Because you can still do like a negative number to an exponent.
You can. Technically, you would have -1 times that number, so you can always kind of rewrite it. So then it's still positive.
If you did like the power of negative, power of 3, then it would still be negative.
Yeah, for the rules, we just establish them with the positive version because, yeah, like you said, the even power of a negative makes it positive. And then the odd is still negative. And so I think we're just kind of eliminating that possibility. Yeah. But yeah, the go-to trick would be just rewrite it. So if you have -3 to the power of 2, for example, you would have -1 times 3 to the power of 2. That makes sense. Okay. We've seen this briefly before, right? Where a to the -n, we can rewrite as 1 over a to the n, as long as a is not 0, because we can't divide by 0. And so we move back and forth between these two notations, depending on what we want to do, right? And so definitely a two-way street on this one, right? And so we need to be able to move back and forth there. If I start over here on the right-hand side, if I want to take the nth root, right, of a, as long as n is greater than or equal to 2, so the second root, third root, fourth root, whatever, then what you can do in your calculator, I think we have a fancy root button where you can take any root that you want, right? But most calculators don't. And so then usually the trick that we use is writing a to the 1 over n. So far we're doing okay. We use this property, the a to the 1 over n, usually if we're trying to simplify things. And so if we're trying to simplify exponents, which we will be doing, then this is a nice property to have. Okay. Another nice property to have up our sleeves is, well, if we let's start here in the middle. If I want to take the nth root of a to the m, then what can I do? I can rewrite this as the nth root of a all to the power of m. And so this power of m can kind of float around, is what that's saying. But really what that means is that we can combine, where is it? We can combine, yeah, just the fourth property, right? The nth root and this power of m, and we can say, and let me just go down here to clarify 5. If I have the nth root of a to the power of m, that's going to be the same as a to the power of m to the 1 over n. And I suspect I'm going to jump ahead to property 8. So here, introduce this one. The reason it simplifies to a to the m over n is because if I can rewrite the powers as being multiplied together, then I am just allowed to multiply them together in the power and simplify. Okay, and so here, by 8, a to the m to the power of 1 over n is the same as a to the m times 1 over n, which is a to the m over n. That's kind of a nice one. I guess it does leverage a later property, but that's okay. For property 6, notice that they have the same base, right? And so they have to have the same base a, but if they do, how you can simplify that is you can, if they're multiplying together, a to the m times a to the n, then you're allowed to add these powers, right? And we've seen that before, and I've kind of snuck it in, but now we see it, why that is. Well, it's just a fact, I guess. I think that one's usually pretty straightforward. but let's talk about why 7 is true. 7 says that a to the m divided by a to the n. Let's work through this little guy. What can I do? I can rewrite a to the n in the denominator as, right, as 1 over a to the n, which makes a to the negative n if I'm floating it upstairs. Okay? And so we'll start there. So I have a to the m times a to the negative n. But notice now that I have the same base, which means that by property 6, right, if I have the same base being multiplied, then what can I do? Then I can say a to the m plus negative n. Which is a to the m minus n. Now these rules are established, and so you don't need to show all this work, right? You're allowed to move back and forth immediately, okay, between these two. I just want to show you where they came from so that they're not so crazy. In case it's been a while. We've seen property 8 already, right? But if I'm multiplying in the powers, then it does just result in multiplication in the powers. If I have two different bases, a and b, all to the power of n, then what you're doing is you're distributing this n onto both of the terms, right? Becomes a to the n times b to the n, right? Once you break out those brackets. Similarly, if you have a over b to the power of n, right? We could work this out and we could say, okay, well, I could rewrite this as a times b to the negative 1, right? And then I could distribute this n inside, right? But really where we end up is just a to the n over b to the n. And so how I think about it, even though there's a longer way to derive it, how I think about it is it just distributes onto each of the terms again. Okay. What happens with a over b to the negative n, right? That's technically 1 over a over b, okay, to the n, I guess. What we can do is if we have a look at 11's more interesting than 10, so let's have a look at 11. We start with a over b to the negative n by, oops, I'll do by 10. This becomes a to the negative n over b to the negative n. Oh. Which is really 1 over a to the n divided by 1 over b to the n by 3. By property 3, this becomes 1 over a to the n divided by 1 over b to the n. A fraction over a fraction, right? Fraction over a fraction, you have to flip the denominator and then you multiply. And so this becomes 1 over a to the n times b to the n divided by 1, which is b to the n divided by a to the n. And then moving in the reverse direction of 10, so by 10, what can I do? I can pull this n outside and simplify it. So then, and I'm gonna need just a little line more. By 10, this becomes b over a to the n. So we need to be really flexy moving between these properties. All right. Finally, 12, a to the negative n divided by b to the negative m. Now I have different powers, right? Different exponents. And so, but I can use the same kind of move, right? I can rewrite a to the negative n as 1 over a to the n, and b to the negative n m as 1 over b to the m. Woof. Fraction over fraction, flip and multiply, and then you simplify. But because we have different powers here, I can't pull the power outside. Oh. Nice. Let's do, I'm gonna add some pages here. I'll move these guys down. Got some examples for us to simplify. I shouldn't have this times in there. Usually I avoid writing the times, and maybe I'll rewrite it. A to the 4, a to the 8 divided by a to the 7. Just because the times, the x as a times as a multiplier looks like, well, an x. And so I don't want it in there, but we want to simplify a to the 4 times a to the 8 divided by a to the 7. And so what we can do, and there's a lot of different ways that you can approach it, and I encourage you to kind of think about how your brain wants to, which move your brain wants to do first, right? And so one option is to get this a to the 7 just floated upstairs, right? And then simplify everything. Another option would be to simplify a to the 4th times a to the 8th to 1a to the power of something, right? And then float the a to the 7 upstairs. What you'll find is you get the same answer, right? And so it doesn't matter which order you do it, but how my brain works is I like to float the a to the 7 upstairs by making this negative. So now I still have the same base, and it's true for more than one base, right? So as long as I have the same, or sorry, it's true for more than one power. And so what I can do is I can rewrite this as a to the 4 plus 8, technically plus negative 7. But if you want to just skip to writing minus 7, that's totally fine. Okay. And so 4 plus 8, which you could have done first, puts me at 12, right? And then subtracting 7, feel like that'll be a to the 5, oops, to the power of 5. And then it's simplified. Nice. What if you have to simplify this little guy? When you see this 1 plus I times 1 plus I and 1 plus I, right? This is the same scenario as we had here, as long as you treat the 1 plus I as one thing. Okay? It'll get really, really messy, although it is tempting. I can see why it would be tempting, right, to do 1 plus I times 1 plus I times 1 plus I and expand this thing. But then you look down the line and you see, okay, then I have a 1 plus I to the power of 9, and it's just going to get out of hand. And so, and we're trying to simplify this thing, not expand this thing. And so as long as you treat this 1 plus I as one thing, right? You can rewrite it as A temporarily if you want, right? Then what do we have? Then we have 1 plus I to the power of 3 times 1 plus I to the power of 9 and times 1 plus I to the negative 6. Doing the same move that I did earlier, right? Where I float everything to the same line, the numerator, and then I simplify. Right? This becomes 1 plus I because I have the same base of 1 plus I, 1 plus I, 1 plus I. So that's why I'm allowed to 3 plus 9. And then should we just skip to the minus 6? Nice. So then I get 3 plus 9, I get minus 6. Gonna go with 6. 1 plus I to the power of 6. And that's simplified. Right? You have to simplify maybe something like this. Oops. Move these guys down. A to the 3, and now we have plus A to the 5 divided by A. Okay? And so I want you to pay attention to that plus because we don't have any rules where we're able to simplify if we're adding even the same bases, right? And so you want to be really careful when you see that plus, because all we can really do here is, yes, we are allowed to expand this 4 inside as long as we put it on both the numerator and the denominator, right? So let's start there. So we have A to the 3 plus A to the 5 to the power of 4 divided by A to the power of 4. Okay. But I am stuck here. A to the 3 plus A to the 5, there's no way to simplify that, right? And so here, this little guy, this all here does not simplify. Because that's A to the 3 plus A to the 5 times A to the 3 plus A to the 5, and then 3 more or 2 more times. Right, and so we're kind of stuck here. One thing that we could do is we could float this A to the 4 up top, but I don't really see it simplifying the equation very much. So we could write A to the 3 plus A to the 5 to the power of 4 times A to the negative 4, but there's no difference in terms of if it's simplified or not. Here, I just want to make a note why it doesn't simplify, because A to the 3 plus A to the 5 to the power of 4 is A to the 3 plus A to the 5, and then I'm going to use the power of technology and paste this. Oops. 4 times. Right. So we're stuck there. So there's really no way to simplify that thing, in my opinion, any more than maybe expanding the 4 inside. But I would argue that this is the most simplified version, right? Because we've pulled this 4 outside instead of having it appear twice, right? It's only appearing once. And so I'd be happy if you just left that one alone. if we have something like this that we want to simplify? X plus 3 to the power of 5 to the power of 3 over 2. Okay. This is going to be, as long as we treat the x plus 3 as one thing, right? Then you can replace it with a temporarily if you'd like, but the power of m over n is really going to be the nth root of a to the m. So what I'm going to do is just keep the x plus 3 to the power of 5 as one thing for now. Okay. And I'm going to keep it inside the root. Okay, I'll do it two ways. Fine. X plus 3 to the 5 to the power of 3 and the second root. You don't have to do the 2 in the crook. I just want to show where it went. The default in this is the square root if you've done a root, but so then what you can do is if you're multiplying the powers, they're allowed to just multiply. And so what you get is you get the square root of x plus 3 to the power of 5 times 3, putting me at 15. Oh. Alternatively, x plus 3 to the 5 to the 3 over 2, you're allowed to rewrite as x plus 3 to the 5 times 3 over 2, which is x plus 3 to the 15 divided by 2. Oops. Multiplying fractions, you're allowed to just multiply across, which means that I have the square root of x plus 3 to the power of 15. So kind of two ways that you could go about it. I defaulted to this way just because it's, I guess, slightly shorter. But maybe this way it's easier to see what happened. And then finally, we want to simplify. So I had different lines before. 6a squared times b divided by negative 2ab squared. Now, simplifying the powers really only works if you have the same base, right? But you can collect the like bases. Okay. And again, I want you to think about, because there are lots of ways to approach this one, right? The simplification of this one. And so I want you to kind of pay attention to what your brain wants to do first, right? And so as long as you end up with the same answer, then you did it, right? And so what you can do is you can say, okay, well, I have A's here, right? And so I can lump them together immediately, right? I can use what property? I can use this property, a to the m divided by a to the n is a to the m minus n, and just immediately smush them together, right? Or what I'm going to do is nice and slow, just bring this a and b squared up to the numerator. What's nice is the 6 divided by negative 2. Because I'm only multiplying and dividing here, I'm allowed to do the 6 over negative 2, putting me at negative 3. So negative 3 a squared b times a to the negative 1 b to the negative 2. This is probably a slower way then if you're comfortable just kind of lumping your A's and B's together, but we'll get to the same spot. So now they're all in the numerator, which is usually where I want to be, right, for simplifying stuff. And so now I'm at -3. And what I want to do is I want to collect my A's together and I want to collect my B's together. So I have A squared plus -1 times B. Technically, B is B to the 1. Right? We just don't write the 1 usually. Oops. B to the 1 minus 2. And maybe what I'll do is I'll just skip to the 2 minus 1. So I get -3, oops, -3. A to the power of 2 minus 1 puts me at A to the 1, and B to the power of 1 minus 2 puts me at -1. Now, the power of -1 is not usually considered simplified. I'd be happy if you ended here, but we should take it one step further and say this is -3A over B. As you get kind of, depending on how comfortable you are working with these exponent laws, right, you could see A to the power of 2 divided by A. Well, what does that do? Let me just copy this. So, or A to the power of 2 divided by A to the power of 1, right? And then, yeah, B to the power of 1, B to the power of 2. So then you cancel these, and 6 becomes -3. So then you get -3A over B left over. Right. Technically, you are subtracting those powers when you're canceling like that, but usually we're just able to go ahead and cancel things out. But until you're comfortable, right, canceling the powers, then maybe just doing it nice and slow is the better way to go. But then as you get more comfortable, you are allowed to just cancel like this, right? Because you are using those properties, right? Decreasing the powers. Nice. Okay, a little refresher on exponent laws. Okay. Any questions before we actually start the section? The new chapter, I should say. Chapter 4, exponential and logarithmic functions. Yeah. If you are working off of the notes that I posted, I did a little switcheroo because it'll be easier to do this example just after we've introduced the notations. I'm saving a little bit of time here. We will do it, but just after I introduce the exponential function. So we start with exponential functions, and then later in the chapter, we'll move into logarithmic functions, which are the inverse of exponential functions. And so exponential functions, things like population growth, which includes bacteria, which is really important for water studies, obviously, right? And so if you're studying bacteria or really anything that grows, typically it tends to grow with an exponential growth formula, right? And so that's why this chapter is especially important for water stuffs. So here we go. So an exponential growth or decay function, and so we can have exponential growth, which you might have seen before, where it kind of starts off nice and slow and then it kind of takes off, right? And gets out of hand, or a decay function, right? If you've got something that decays over time, so a lot of drugs decay over time, or the potency, kind of minerals and things like that, they decay over time, right? And so we could have a decay function as well. So it's a function that grows or shrinks at a constant percent growth rate. Now, there are two ways that we can write this equation. I'm gonna just zoom in here. We could write f of x is a times 1 plus r to the power of x. Okay? Now, this power of x is what makes it an exponential function. Has x in the power. Right? Trying not to just call it the exponent, but it is. But sometimes it's better to have more terminology. So this power of x is what makes it an exponential function. Now, f of x says that x is the input, right? And so now the input, or what goes on your x-axis, is in the power. And so what we have, the 1 plus r is going to be, the r is going to be the rate, okay, the growth rate, or potentially the decay rate. And a is going to be the initial value. So we have where a is the initial or the starting value of the function, right? How many bacteria did you have to start, right? And then what's the rate that it's growing at, and for how long usually, right? How long did you let this go on for? And so then you can find the population size after some amount of time, usually. And so R is the percent growth or the decay rate written as a decimal, right? Which means that we have to do R percent divided by 100%, which is just R. So usually we talk about rates as percentages, right? Growing at 4% per year, right? But then, so for example, 4% means that R is 0.04. So for our math, we have to use the decimal version. I'll highlight that as a decimal. Another way that we could do it, and we've seen this earlier, or kind of this, oi, what happened? I did something weird. There, back on track. We saw this before, right, where we had maybe something 1 plus I, or something crazy 1 plus R. What we can do is we can just replace it with one value, right? And so we can replace that with a B to simplify the equation a little bit, okay? Where B is just 1 plus R. Now it depends on what information you have, okay? That's going to determine which one of these equations to use, okay? So if you're given the rate explicitly, then of course using 1 plus R is a nice base. But if you don't have the rate, then using B is going to be a little bit nicer, okay? And so we'll see examples of both, but usually we tend to use A times B to the X, okay, as kind of our default. Okay? But B is just 1 plus R. Okay? So B is going to be the growth factor or the growth multiplier. And so it's not the growth rate, but it's a growth factor. And we do have a little note here that since powers of negative numbers, which we talked about earlier, right? Since powers of negative numbers behave strangely, we limit B to positive numbers. And so that's going to be true for the rest of the chapter. So I'm going to say b has to be greater than 0. If it is 0, then everything goes to 0 and there's nothing of interest here, right? And so that's why it's strictly greater than 0. So what does this thing look like if we have a linear function? It would look like this, right? Y equals mx plus b, or a equals mx plus b in this case. And then we can have an exponential function, which starts off looking similar, right? Starts off at a starting point and it kind of takes time to grow. And then once we hit some power of x, all of a sudden things start taking off, right? And so that's what an exponential function is going to look like. Okay. A decay function, let's see here, I'll use orange. A decay function might look like this. Decay would still have the form ab to the x. It's just that the b would have a different property, right, which we haven't introduced yet. But so both the exponential function, just in general, the growth, right? So here we have a growth function, and here we have a decay function. But notice that they just start at different starting points usually, or they can start at the same, I guess. But then the decay, of course, goes down until it's gone, right? Whereas the growth just keeps going up towards infinity. Okay. These numbers are from 2008, which is now a long time ago, I guess. Remember it like it was yesterday. But when we talk about exponential functions, we're often talking about populations, right? And so India is the second most populous country in the world, with a population in 2008 of about 1.14 billion people, which is a lot. The population is growing by about 1.34% each year. And so we might ask if we can find a formula to model the population P as a function of time T in years after 2008, if the population continues to grow at this rate. I'll clarify that they mean exponentially. Populations grow exponentially. First thing we want to make a note of is that T is the time in years after 2008. So T is going to be the year minus 2008. We want to find a formula for the population size as a function of T, right? So we've defined T as the year minus 2008. And so now we're given the rate. Let's pick that one up. So we're given R is 1.34%, which means that R is going to be 0.0134. Maybe I'll do R%, right, as a percentage. Okay. For our calculations, we must use the decimal. That's true for almost all instances of percentages. You have to convert them to the decimal first. I think hilariously, there's even a percent button, but I can never remember if it's 1.34 and then you hit the percent button. Yeah, and then it converts it to a decimal. But it just divides it by 100, so I don't know. But it's there. So that's nice. If you're ever unsure. Okay. Now we're starting in the year 2008. Okay. And so what we are told then, oops, wrong color. It's not that important. We're given that the population at t equals 0 must be 1.14 billion. I'm going to drop the billion because that's crazy, right? And then just add the billion once I have a population, right? And so here, t equals 2008 minus 2008 is equal to 0, right? And so in 2008, the population size was 1.14 billion. Billions, nuts. So then, since I have a rate, right, that's when I'm more tempted to use this version of the formula, right? Because I have an R explicitly. And so then I can use this little guy here, copy, to build my formula. Now I want to build a formula for the population size at some input time t, right? Which is going to be the time after 2008. Which means that this power is going to be a power of t, right? Because that's my input. And so maybe to make use of this arrow that I copied and pasted in there, right? This x is being replaced by t, more specifically for this question. And we're finding the population size. Now A, remember, A is the initial or the starting value of the function, which is really going to be p of 0. Right? And so here, this means that p of 0 is my starting point, 1.14, must be A, by definition. And so I have, I'll write it out in general here, A times 1 plus R to the power of t, but p of t is 1.14 times 1, plus 0.0134 to the power of t. I'm curious to know, what if we tried, so now try finding the population in 2025. P of 2025 minus 2008. Math. 17. (1.14) times 1.0134. Notice that we'll usually just simplify the 1 plus R into basically a B, right? And so that's what the B is the 1.0134 to the power of 17. So I have 1.0134 to the power of 17 times 1.14. I get 1.429 blah 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 billion. And now we can Google that. Let's see how far or of it's close. It's guessing I want to know Iran, but I want India. It should have been listening harder. Hey, not bad. 1.451 in 2024. They jumped a little. It's a little higher than we predicted, but not bad. Oh. Nice. Okay. Now, I have these in the notes already. Wait. Let's just. They were clearly written with a different line spacing. It's driving me nuts. Huh? So what we've seen, oh, any questions about this one? Oh, I'll make a note. In 2024, P of 16 was actually, what was it, 1.451 billion? Just for fun. But we did a year later and got a lower number, so something happened. We're just growing crazy. In general, what we're going to find is this scenario, right? Where A is the initial value, which means that f of 0 must be A. Okay? Which also means that this function is going to pass through 0A. Okay? Which means that on the y-axis, it's going to pass through y equals A. Okay? Which is a nice thing to keep in mind. It's kind of our starting point for our curve, right? Just as for lines, right, where we had the y-intercept, right? This is basically our y-intercept. Still. Huh? We've got our r, and then the variable is in the exponent, which we've already talked about, right? Making it an exponential function. Now r, right here, is a rate of growth if r is between 0 and 1. Percentages are between 0 and 100, right? And so then converting to a decimal, it's between 0 and 1. And it's going to be a rate of decay if it's a negative percentage, right? Which means that it's going to be between -1 and 0, right? So if r is negative, then it's decay, and if r is positive, right, then it's growing. Right? What we're going to find is that we can write that f of x is a times b to the x, right? We said, okay, well, more likely we'll probably just be using this simpler version of the equation, right? Where b is 1 plus r. Okay. And so I feel like I changed these before class, but oh well. So if r is between 0 and 1, then we have growth, right? And so if r is between 0 and 1, then 1 plus r must be greater than or equal to 1, right? Which means that b must be greater than or equal to 1. So if you have a b that's bigger than 1, right, then you're going to have growth. Okay? Whereas if r is negative, right, then we know we have decay, earlier. Okay. And so it's between -1 and 0. So that means that B is going to be between 0 and 1. Right? And so then, right, B is between 0 and 1, tells me that I have a decay here. Right? And so, and I've got a note saying that we force, there, we force this B to be greater than 0. But it would also be 0 because the rate can't be less than -1. Oh, but we do force that, just to be clear, that B has to be greater than 0. Right? Oh, that's what my note is about. We force this instead of 0 less than or equal to B. Should clarify that. Because R can be greater than or equal to -1. Now, if R is equal to -1, then B would be 0, but we force it to be greater than 0. That's what my note was about. I have to decipher my, don't know why I decided to keep those notes in there, but maybe I just forgot to remove them. There. So depending on what B is, right, you can translate that to the rate, right, and look at the rate, which I think is more intuitive, right? If it's positive, it's growing. If it's negative, it's decaying, right? But knowing their relationship will be good. If tuition is currently $1,050, wouldn't that be nice? And if tuition has been increasing by 7% per year, and I've added exponentially because we're in the exponential chapter, it's kind of implied. But what we want to do is we want to predict the tuition in 5 years. So what we have, or what we're given, is that the tuition at time 0, right? And if we want to find the tuition in 5 years, and you can use F if you want. I just want to use the T because it's nicer to look at. So the tuition right now is $1,050. It's not, probably. I don't actually know what it is, but it's more than that. So the tuition at time point 0, we're told, is $1,050. We're also given that the rate is 0.07 per year. So we can build our bare bones formula. Now, if I have the rate, I'm going to use the formula that has the rate in it, right? Generally, it'll look like f of x is a times 1 plus r to the power of x. Now, I've thrown in a t for tuition instead of an f, and I'll do a lowercase t for time in years from now. Kind of typical. A times 1 plus r to the t. This t of 0 makes a, right? The initial, the starting point. So a is 1,050. We're told r is 0.07. So 1 plus 0.07, which means that b would be 1.07, right? So it's greater than 1, which means it's growth, but we also see that from the 0.07 growth to the power of t. So now we have this equation for the tuition, and we can plug in any t we want, but we want to find t of 5. Which is 1050 times 1.07 to the power of 5. Starting with the 1.07 to the power of 5, and I'll make that clear here. 1.60578146 times 1050. I get 1686.07055. Now this is money, and for money, we round to 2 decimal places, right? And so here, 1,686 and 7 pennies in 5 years. Nice. Good.
I got a different number. You're so right.
Oh, really? Uh-oh.
72. Yes, I'm 68.
Strength in numbers. Well, I already committed, so I have to do it in a penalizing red. 1 point, I don't know what I did. 1.4025511731. Is that what you guys got for that power? Oh, times 1050. Just keeping you on your toes. Thank you. 68 pennies. Nice. Not sure what I did. I guess I could reverse engineer it, but that's okay. All right. What if we have to interpret this equation that says P of t? Now, usually if we're using P, it means a population size, and T is presumably time in years or whatever. P of t is 1,000 times 0.83 to the power of t. And so what we can say is, okay, well, kind of a go-to thing is that the population at time 0 must be 1,000. So if I plug in 0, I get 0.83 to the power of 0. Anything to the power of 0 is 1, and so then I'm left with just 1,000. Now this 0.83, though, is 1 plus r, if you want to translate it. Right, or if you remember, if b is between 0 and 1, then it's decay, but just to emphasize that that's the case, right, then we know that this is going to be, so 1 plus r is 0.83, right? Which means that r is negative, oh, minus 1, negative 0.17. I want to muck it up. Which means that it's decaying at a rate of 17%. And so a population, I'll make a note here that assume t is in years. Right, it's not clear from the equation, but it doesn't matter. It could be per minute, right? But let's just assume that it's in years. So a population at time t started at 1,000 and is decaying at a rate at a rate of 17% per year, or whatever we assume t is. Okay. Notice the negative is the decaying part, and then the rate is just 17%, right? So we don't say negative 17%, we say it's decaying at 17% per year. Nice. Good. What if we have to find an equation for these things? So find an equation for an exponential passing through the points 0, 3, and 318. We know how to find equations of lines passing through 2 points. What did you have to do first? You had to find the slope, and then we used one of those points, right, to find the intercept. And that's how we constructed our lines. And we're going to do a similar thing for exponential functions, right? So if we remember our general exponential function, f of x, and I'm going to use a b to the x, because there's no mention of a rate, and so it's going to be easier to work with b. Okay? And so here, I chose b instead of, instead of 1 plus r, since there's no mention of r. No? These points tell me that f of 0 must be 3, and f of 3 must be 18. Okay, that's nice. It's also nice because a is the starting point, right? Which is f of 0. And so here, recall that a must be f of 0. If you don't remember that, right, or try f of 0 is a times whatever b is to the power of 0, and that is going to have to be 3 by that point, 0, 3. B to the power of 0, or maybe I should write it properly, not with the 3 on this side, but I'll replace f of 0 is 3, a b to the 0. Now b to the 0 is just 1. And so here, therefore, sloppy, therefore, a must be 3. So you don't have to remember that a is f of 0, but it saves you a little bit of time, right? And you're allowed to jump that hoop. Doing it this way, though, is going to be nicer because then it really doesn't matter which points you're given, right? I don't need to give you the 0, 3. I don't need to give you the y-intercept. It's just our first example of constructing these things, and so it's nice. We don't need it. So now we can start and we can build up f of x is a b to the x. Now I'm going to replace my, f of x is 3b to the x. But we're also told that f of 3 has to be 18. And so that's what we're going to use to solve for b. So now use f of 3 equals 18 to solve for b. Okay. F of 3 is 3b to the 3, which means 18 must be 3b to the 3. How are we gonna solve this? I have to first divide both sides by 3, so 18/3, which is nice. And I'll try to keep it on the same. So that's 6 is b to the 3. And I'm gonna need more room anyways. Oops. Hey. So then b is going to be the third root of 6, which I'm pretty sure is nothing to write home about. That's okay. So then b is the third root of 6, or if you prefer, 6 to the 1/3 does the same thing. I think in this scenario, because I'm trying to write out a general equation for f of x. So now, f of x is 3 times 6 to the 1/3 to the power of x. Now, by those exponent laws that we talked about, right, 1/3 times x, I can simplify that to make x/3. And so then I get 3 times 6 x/3, or to the power of x/3, I should say. Notice that the x/3 is just on the 6, and so you want to make sure you use some brackets there. And more I look at it, the uglier it is. X/3. Nice. Guess we can graph it to make sure. Three times 6 to the power of x divided by 3. Oh, my Desmos is acting up, of course. Ugh. Just restart it, I guess. 3 times 6 to the power of x divided by 3. Close this bracket. What do I want to confirm? I first want to confirm that it goes through 0, 3. And then how can I confirm that it goes through 318? I can draw a line at x equals 3 and make sure that it crosses at 318, which it does. So mission accomplished. There. Bring this in. So that's what that exponential function would look like. Now, we're already here. What if we do another one where I don't give you the y-intercept anymore, right? I don't give you where x is 0, but we can still work with that. We want to find an equation for an exponential passing through the points 2, 5, and 4, 1. So here, this tells me that f of 2 is 5, and this tells me that f of 4 must be 1. We'll start there. what do you sense about this equation, right? When x is 2, we're up here, let's say. And when x is 4, it's down here. So I'm expecting a decaying function, right? And so it's nice to kind of have an idea of what you're expecting this to look like, right? And so we're expecting something like this. So let's see. What's the first thing we're gonna do? Well, we can start staring blankly at the page and say, well, f of x is a times b to the x. I don't have an r, right? If I did, from the points, I expect it to be negative, right? But what does that mean about b? I'm expecting b to be between 0 and 1, right? So we've got these expectations, and let's see what we can do. F of 2 is equal to 5. Let's start there. And so if I plug in x equals 2 here, then I should get 5. Right? So let's start with that. F of 2 is a b to the 2, which I'm going to do this, should be equal to 5. I don't usually like to write the equal signs across like that, but I think it's going to look nicer in the end. And maybe I'll put it over here. And f of 4, which is a b to the 4, must be 1. What I can do is, what if I solve for a in the first one, and then I substitute that a into the next one, right? Kind of turn it on itself. So here, solve for a, we get a is 5 over b squared. Now, substitute a equals 5 over b squared for a. So then I get f of 4. I'll start with a b to the 4 must be 1, where a is going to be replaced by 5 over b squared times b to the 4 equals 1. Notice that I've ditched the f of 4 because it was just a placeholder for 1, really. But now I've substituted the a, and I'm only left with b's now. That's nice because it's going to let me solve for b, right? And so now, solve for b. Using our exponent laws, right? I've got b to the 4 divided by b to the 2, which is technically b to the 4 minus 2, right? And so we can start there and we can say, okay, well, this is the same as b to the 5 times b to the 4 minus 2 is 1, which means that 5b to the 2 is 1, which means that b squared must be 1 over 5. Now remember, I'm solving for b, but when we take the square root, b is the plus minus square root of 1 over 5. However, b, remember, has to be greater than 0. We're forcing it to be greater than 0. And so what I'm going to say here is we ignore the negative option, since b must be greater than 0. So then there's only one option. Therefore, b must be the root, positive root of 1/5. Which is a number, but I'm just going to keep it as the root of 1/5 for a little bit. So now I have this b component, right? Now I can go back to a, but remember a, we solved for a earlier. A is going to be 5/b². And so now, which color have I been doing my commentary in? Now use a equals 5 divided by b² to solve for a. A is 5. Let me make sure that I'm using b². Yeah, good. So a is 5 divided by the square root of 1/5 squared, which gets me to 5/1/5. Right? And you can simplify this, right? You've got I think we're pretty comfortable with if we take the square root and then square it, they just kind of dissolve, right? But technically it's because the root is a power of 1/2 times 2. 2/2 makes a power of 1. And so that's technically how they dissolve. Okay? But we're left with a is 5 divided by 1/5. Now 5, I can rewrite it as a fraction, right? 5/1 divided by 1/5. So when I flip and multiply, and I'm gonna just write across because technically 5/1 times 5/1, I get 25. Okay, I won't, I'll add a page. Teacher. So a is 25. Therefore, f of x, which is in general a times b to the x, must be 25 times b, which we said is the root of 1/5, right? I don't think 1/square root of 1/5. No, it's nothing nice. So I'm just going to keep it as the root of 1/5. To the power of x. But notice that the root of 1/5 is approximately, now I ditched it, 0.4472135,955, which would be decay, right? Because it's between 0 and 1. And since b is between 0 and 1, it is decaying. Which is what we expected, right? And you can graph it to make sure it's going through those points, but it's behaving how I expected it to, so I'm gonna leave it there. Any questions about that one? Nice. So I will need you to be able to take 2 points and construct an exponential function that goes through those 2 points, just like we did for lines. Yeah.
For that one, you can write it also like 1/5 to the x over 2.
You can.
Okay.
Yeah. So here, or 1/5 to the power of x divided by 2. X. Which might be cleaner looking, actually. But I was trying to make it mimic the b to the x, I guess, but yeah. But for evaluating, I think this one would be nicer. All right, what about it? If x is 2, then you're off to the races. All right. Nice. Now, kind of maybe not in wet, but in life, finance is a big part of math, right? Money problems. And so a really common formula that we use is the compound interest formula. To give you a little bit of background, if I have some initial amount that I'm investing, let's say I have $100 and I take it to the bank and they say, oh, we can offer you a rate of, let's make it good, 4%. I would be thrilled to have them give me 4%. They're not going to, but let's say it's going to grow at 4%. Now, what banks tend to do is at different intervals or frequencies, they compound your interest. And so if it's compounding monthly, for example, then at the end of every month, what they do is they figure out how much interest you've earned, and they tack that on to the initial amount that you deposited. And then you earn interest on the compound of the two. And then the next month, you earn a little bit more interest and it kind of compounds and it snowballs. Okay? Surprisingly not as fast as you would like it to snowball, but it does grow and you earn interest on more and more money, the more interest you earn. And so that's what the compound interest formula does. And it's just kind of nice to know just some financial math. We're just going to dip into it with this formula because it is a really common exponential growth formula. Sadly, they also compound the interest that you owe if you owe them money. And so, and usually they're okay with a higher rate for that. But anyways, we're going to use the notation A of t. A of t is going to be the account value. And so at some time point t, we can calculate the account value. T has to be measured in years. A is the starting amount of the account, which we often call the principal amount. And R is going to be the annual percentage rate, which is the APR, which we also call the nominal rate. But usually, if banks are advertising, they advertise the APR rate, which is the annual percentage rate, is what it stands for. Which is also, because it's annual, is also why T has to be measured in years so that they match. K is what we're going to use to denote the number of compounding periods in 1 year. So how often do they check in to figure out how much interest did they earn and tack it on, right? And so some common values of K, oops. So the number of compounding periods in 1 year. So if K is 1, then it's compounding annually, which can happen. Right? So at the end of each year, they figure out how much interest you earned, they tack it on to the principal amount that you invested, and then for the next year, you earn money on the principal that you invested as well as the interest that you earned from the previous year. K equals 2 is semi-annually. I've looked at my own mortgage paperwork, and it seems that banks tend to compound semi-annually, right? And so mortgages especially tend to be compounded semi-annually. Another common one is if K is 4, then we're compounding quarterly. If K is 12 times per year, then we're compounding monthly. That can happen at the end of each month. I feel like a credit card would maybe compound monthly. They might compound daily. K equals, we'll do 52 for weekly. Since we're not doing a deep dive into these, right? As long as you remember that K is the number of compounding periods per year, it'll say something like compounding 6 times per year, right? Which isn't a common one, but then K would just be 6. And then K is, we're gonna assume 365 for daily. There's leap years and stuff like that, but we ignore those. Okay. So some common values just to be aware of, right, are these 6. There's others, but like I said, we're not going to spend a lot of time with this formula, and so who cares? Who cares? As an example, if you invest $1,000 in an account that earns 4% per year, compounded quarterly, how much is in the account after 5 years? And as a follow-up question, whoops, how much interest did you earn? And so let's see here. We've got our formula that we want to use, and maybe I will keep this just on the same page here. There. This $1,000 is the initial amount that you've invested, and so that's going to be your A, okay, your lowercase a. So we're given A, lowercase a, is 1,000. Okay. We're also told that the rate is 0.04 per year, but it has to be per year. And we're told that it's compounding quarterly. Compounding quarterly tells me that K must be 4. So 4 times per year, which confusingly is every 3 months, if you think about it. Right? But don't think about it. And we want to find A of 5. So we've got all the components and we can plug those into our formula, right? A of t in general is A times 1 plus R divided by K to the power of K times T. The T is still in the power, it's just being multiplied by K in this case. And we want to find, I'll do a general A of t. We decided, okay, the initial amount that I've invested is $1,000 times 1 plus a rate of 4%, so 0.04 divided by 4, that's nice, and 4 times t. Just keeping a generic t for now, just in case you wanted to work with different time periods. A of t simplifies to 1,000 times 0.04 divided by 4 is 0.01 and then plus 1. So we can rewrite this as 1.01 to the power of 4 times t. Right? It's growing, just not very fast. Right? And so therefore, a at 5 years is 1,000 times 1.01 to the power of 4 times 5. 1.01 to the power of 20. 1.01 to the power of 20 times 1,000. I get 1220.19004, which is money. So I'm going to round to 2 decimal places. 19 pennies. That's nice. How much interest did you earn over 5 years? $220.19. Right. That's the spirit. Yeah. Now, yeah, this is the real homework. Go out and find a bank that gives you 4%. That's the real homework, I guess. And if you find it, let me know. How much interest? A of 5 minus A of 0. 12, 20, 19 minus 1,000. You don't have to use the formula. It's pretty straightforward. Take away whatever you invested, and the rest is interest. Over 5 years. Nice. Let me just, uh-oh. Uh-oh, she says. Uh-oh. As an example, if we have $1 that's invested at 100% interest for 1 year, right? If we're compounding annually, then we would have 200 or 200, we would have $2 at the end of the year. If we're compounding, so here, what we're saying really is we're compounding k equals 1, k equals 4 times, k equals 12, k equals 365, k equals, I don't know, hourly, once per minute, once per second. I give up. Dot, 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 dot. There. The idea is, if you break it down and you have this compounding happening more and more and more frequently, then, and you can use the formula and you can do these calculations if you want to, but the idea of what's happening here is that this value is approaching 2.7182828 blah 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 blah, which you might, so it's approaching, you might remember as E, approaching E, Euler's number. Everyone wants to say Euler, but it's Euler. And just so, oops, not another E there. It's Euler's number. And this is pronounced Euler, not Euler. So Euler's number, E, named it after himself, I guess. is a letter that's used to represent the value that 1 plus 1 over k, right? And so remember the rate here, R is 1, right? 100%. So the rate is 1 in this specific case. So 1 plus R over K makes 1 plus 1 over K. And then T is 1, right? And so here, T equals 1. Now, as we break down K, right, on smaller and smaller and smaller intervals, right? So K is 1, 4, 12, 365, and then even bigger, 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 right? What's happening is we start to slow down at E, which is just like pi, an irrational number. So it keeps going forever and ever and ever. But for some reason, people don't tend to memorize it as commonly as pi. Right? Everyone knows pi continues forever, but so does E. Okay. And so E is roughly 2.71828. Blah, blah, blah. Okay. So here, but we have an E button on your calculator, which I suspect uses an approximation, of course, but more than we have. Okay. And so that's where it comes from. It's just letting K approach infinity in 1 plus 1 over K to the power of K. Okay. Bringing me to the continuous growth formula. Okay. Now, continuous growth, right, is going to have a very similar form to what we have been seeing, right? Except that now we do a little switcheroo, I guess. F of x is A, where A is still the starting amount. That's nice. And then we have E, which is just a number, right? Just like B was just a number. But then we have R, which is the continuous growth rate times X. Okay, so the R is up in the power. And what I want to do is, oops, not do that. Just do a comparison of these values. Because if I tell you, hey, I'm going to compound your interest continuously, right? It's kind of mind-boggling, right? So you're earning interest, but then continuously it's being added on, added on, added on, added on. But it takes your rate and it splits it up on the continuum. So it doesn't really make a huge difference. And to see that, right, we're going to do a problem where you deposit $1,000 in an account that earns 1% compounded monthly, right? And we want to find the amount in the account after 10 years versus the same $1,000 at the same 1%, but compounded continuously. And we want to find the amount after 10 years. Right? And then we'll look at those two and compare them. And kind of disappointingly, they're not going to be that different from each other. Okay. So I'm just going to highlight the only difference between these two questions that we're about to do. First, we'll do monthly, and then we'll do continuously. So we have A of t is A times 1 plus R over K to the power of K times T from our formula. Okay. And we're told that the initial investment is 1,000. We're told that R is 0.01. And we're compounding monthly, which means that our K is going to be 12. And we want to find A of 10. I'm just going to jump right to it. A of 10 is 1,000 times 1 plus 0.01 divided by 12. Now I'm second guessing that I have the form. I do. I just did a whole section on financial math in one of my other courses, but we're using a slightly different version of the formula, and so I'm getting thrown off. They do the same, they just use different variables. Do the same thing, I should say. There. A of 10 is going to be 1,000 times, and I'm gonna simplify, so 0.01 divided by 12 plus 1 is very small. 1.000833 repeating. I'm gonna make sure that I keep all those decimal places in my calculator, because people don't like when you round unnecessarily with their monies. They get really upset usually to the power of 120. But that's okay, we can just keep all our decimal places. 1.105. 1,24896, and it keeps going, but if I times it by 1,000, it's not until the very, very end, 1105.124896, that we can round to 2 decimal places. Oops, 1105 and 12 pennies.
Do you want us to show every step like that, or can I just answer it?
You can just answer it. So here, these, let's see, ideally, I'd love to see the full decimal just to make sure that you got there. And then the rounded value, but this work is optional. So what I want to see is I want to see the empty formula that, so you show me that you know which one to use,
Yeah.
right? Show me the values all plugged in where they should be.
Yeah, because I've just been answering it from there.
Yeah, that's great. Then from here, you're allowed to jump down to here. But I do want to see the unrounded one and then the rounded one. Awesome. Yeah, so just so that someone looking back can follow along in the notes, I write them all, but or a lot of them. Feels like I'm out of time. Let's do the continuous one so we can compare them. Or use it for review next week. Ah, review. Oh, I keep sorry. Sorry. Mea culpa. Happy Halloween. See you on Tuesday.